12.8 Length of curves. Using a vector-valued function, we can predict the position of an object. What if we wanted to know how far an object travels over a given interval of time? For example, suppose we would like to find the flight distance of this eagle for the first 10 minutes of flight. We're given this definition of arc length, and notice that it involves speed. When speed is constant, we know that distance is the product of speed and time. If speed varies, then we can use the product of speed times a small increment of time. So for each increment of time, there will be a different speed. So we go speed times time for each of those increments and then add them up. That's an integral process. Find the length of a complete hypocycloid. We're going to find the length of the hypocycloid in the first quadrant, and then we're going to multiply the result by 4. You'll see why in a minute. To find speed, we first need to find velocity. Then we find speed, and then we can find arc length. Speed is given here, velocity is given here, and then speed. Clean it up a little bit, and we get this radical. This is where making our decision to work only in the first quadrant is of great benefit. If t is in the first quadrant, then both cosine and sine are non-negative. They're either 0 or positive. So we can, if we stay in the first quadrant, we can take the square root of this. Taking the square root, we get 3 sine t cosine t. Remember, we're going to multiply the result by 4. So we're looking for this integral. Use the double angle formula, finding the antiderivative, and evaluate. 6 units long. Find the distance traveled by an eagle rising on this path given by a helix. Same process. This is the velocity and the speed. Notice that the speed is a constant value. So finding the arc length is going to be very straightforward. In 10 minutes, the eagle travels about 2,690 feet. Let's talk about arc length in polar coordinates. If you'd like to derive this formula for arc length, all you need to do is look at the relationship between polar and Cartesian coordinates and then use the definition of arc length. Let's do an example. Find the arc length of the cardioid. For the cardioid, theta is going between 0 and 2 pi, but we're going to use symmetry again. Notice that when theta is between 0 and pi, we get the top half of the cardioid. First, let's set up the integral. We find f, we find f prime, square each, and then add them together. Do a little bit of cleaning up, and we get this expression. Next, we're going to use the half angle formula. If you look at the formula, you'll see that we need to take the square root of this expression. And so we, again, like I said, we're going to restrict the values of theta. If theta goes between 0 and pi, then cosine of theta divided by 2 is going to be positive or 0. So we will find the arc length for theta going between 0 and pi, and then multiply the result by 2. We take the square root. Notice the bounds from 0 to pi. Also notice that we're multiplying by 2. Then when we take the square root, we have a fairly easy integral to do. And the length of the cardioid is 8 units.